Hello, it's Andy here, and I'm just making a short video to give you an update on the software tool that we're working on. The tool's called Engentica, and I think you'll find our updates kind of exciting this week. I'll show you some integration with large language models and what that might be able to do for EMC debugging and troubleshooting and analysis. So yeah, without further ado, what you're seeing here is our import process. And we work with bill of materials, currently with Altium, exports from Altium. So bill of materials, a netlist file. It's actually the wireless netlist file. And we're importing schematics in PDF format. So during the import process, we do a lot of analysis and synthesis of the information. And here you can see mapping of the BOM into fields that we can work with. So there's a little bit of manual work here. Hopefully we'll be able to automate that in the future. But right now there's a bit of manual work. Here we are assigning component types to reference designators in the BOM. So it found most of them automatically. It just missed the ferrite beads. And then here we're assigning PDFs, that's data sheets, to the integrated circuits found in the design. And because I've imported this design before, it's already mapped them. So it's just using the existing maps. And we use that to extract a lot of data and synthesize into usable data for design rule checks and some more features that you'll see in a minute. But what you can see here is that we have markers overlaid on the schematics. So the blue markers show a design guide available, and the yellow markers show a warning. We also have red markers as well, showing risk areas. And this particular design is OpenRex by Robert Fernack, and it's an extremely good design, no major warnings here. And so throughout the design, you'll see guides served up that show risk areas and design guides that can be extremely useful for engineers as a training tool and to avoid potential pitfalls. And here I'm just showing our layout viewer. So this is an ODB layout viewer. Just so you're aware, the tool is it's a Microsoft Windows tool, so it isn't actually an app on the internet, and we did that for security purposes. We want design files to remain on the user's machine. And as much as possible, we're doing processing on the user's machine as well. So a Windows-based tool. But what's really cool that we've just got up and running as of last week is we've set up an MCP server to allow our tool to talk with Claude Desktop. And ultimately, we may be able to set up a local LLM to perform this function. But right now, for rapid development, we're talking with Claude via the API. So Claude is now talking with the design that's open in the tool, and we've asked it to just evaluate what the design is and get familiar with the project. So it is autonomously querying the tool, and it's saying we can see a new project. That was the name of the project I put in. It's found the components and the schematic and the BOM, and it's just summarized what that is, and it's also found some of our EMC analysis, and it says what that might be useful for. So here I'm just making up a radiated emissions problem. I've said there's an emission failing at 240 megahertz and 480 megahertz, and I've given it an extremely broad question of please help me to debug it. So bear in mind this is a very early prototype, so the analysis at this point is the worst that it'll ever be, but it's actually reasonably useful. So right now it's querying the design, and you'll see it going through a number of queries, and it's looking for components that may be a source of those sorts of emission frequencies. And that's actually pretty good. That's kind of what we would do as EMC engineers or consultants. We'd look for potential sources. We'd search through data sheets looking for clock frequencies. And so it has actually found some sources, it says. It's looking for switching regulators and high frequency ICs. It says it's getting a clearer picture. And then it's going to query those ICs for more information. So there's still some communication issues, but it's able to work them out. And now it's looking at connectivity and the relationships between the components, which our data model facilitates. So this is all really good and kind of to be expected for troubleshooting. And so now it's kind of zoning in on a DDR3 memory interface. And it's hypothesized that that could be the source. And it's giving an analysis and some suggestions for verification and tracking things down further. So it's suggesting near-field probing and some strategies for mitigation. So that's actually really good as a hypothesis. But for people who've worked with USB before, you'll probably recognize those frequencies as standard data rates for USB 2. So I've just asked it a question: are there any USB interfaces in the design? So it's checking for that. And what we'll be doing over the coming weeks and more is to augment the existing data with more and more standardized design rule checks and data augmentation. So a lot of this stuff will be surfacing proactively and deterministically. So the LLM will not have to go through this kind of process. Or the data that we surface will make the LLM much more effective. But essentially, it has found the USB interface, and it's highlighted that as a much more probable source of the emissions, and it's given some ideas for mitigation based on that. So now I'm going to ask it a bit more of a broad question to evaluate the decoupling strategy on the board. And so Claude is now going to query the capacitors across the board and evaluate their usefulness. So as you can see, it's successfully querying, and it's collating the information. And now it's going to generate a report for us. First, it's looking at more filtering. It's collating some info on ferrite beads and putting that together with the capacitance information. And so here's a report, which is reasonably comprehensive. Another thing we can do with this is to construct queries that we can then store locally and have executed on every design deterministically. So right now, this is somewhat subjective and variable, but we could actually capture this and integrate it as a deterministic design review if we like it. So this really adds some power to our design tools, and it's intended to really help engineers to surface issues before hardware is designed, or even if you do have an EMC or EMI issue, it can absolutely help you to track down the source and guide you on on fixing issues. So just as a last test here, I've asked it just a very general question, what about ESD protection? So now Claude is going through the design data, and it has successfully found some ESD protection diodes. And actually right now we're working on the layout data extraction. So we'll be augmenting this existing data with spatial data so that we can answer much more in-depth questions that involve both schematic and layout data. So we'll be able to tell, whether ESD protection is close to connectors, whether the routing is correct, as well as whether the ESD protection diodes that we've selected is sufficient. So this is going to be quite a powerful tool for hardware engineers to help with both training and upskilling and design rule verification, as well as troubleshooting. So we're excited to continue working on this. We're looking forward to launching a product. But in the meantime, let me know what you think. Think of applications for this. What do you like about this? What don't you like about this? We're excited to hear what your thoughts are and what suggestions are. But at this point, we have a good framework in place, and we're positioned to really accelerate development with this integration now as well. So we're super excited, but happy to know what you think.